Hello, welcome to the third part of our frequency response playlist. In this video, we are going to look at Bode's rule. Bode's rule gives us a very short way or easy way of writing or plotting out the frequency response of a system. Before, let's do a quick recap on something we should already know. Now, the transfer function of a system could be written in this form, where this is the pole zero frequency and these are the pole frequencies. Now, from this system or this equation, we could see that if the frequency of the system reaches a pole frequency, then we can let's just take a first order system. If the frequency reaches a pole frequency, then from this term we see that the gain would increase. And if the frequency reaches a zero frequency here, then the gain would increase. And if the frequency reaches a pole frequency, the gain will reduce. So assuming S is equal to omega P1, then we are going to have the gain reducing by √2. And if S is equal to omega WZ1, we are going to have the gain increase by a factor of √2. Okay, so let's see what Bode tells us. So Bode tells us that if you have a system, assuming the system goes to at very low frequency, so you have a gain something like, say, GMRD as your gain. Then as the frequency increases, so this is the frequency term, as the frequency increases and reaches a pole frequency, then the gain will begin to reduce by minus 20 decibels per decade. Now, what this simply means is that if you further increase, so from the pole frequency, if you further increase the frequency by a factor of 10, so the per decade part means if I move here where the frequency is now increased, of the frequency of the system now increases from the pole frequency to W pole times 10, so that's 10 times fold of the pole frequency, then it means that the gain of the system is also going to reduce by a factor of 10. So the gain now becomes GMRD over 10. So that's what Bode tells us. Now, if we come across another pole frequency, a system, assuming the system has two poles, then we reach another pole frequency, we call that pole frequency 2, then the gain would further reduce, so the slope will further reduce by another minus 20 decibel per decade, which will be a total of 40 decibel per decade from the original reduction. Okay, but what if we reach a zero frequency? If we come across a zero frequency, then the opposite would happen. Remember, zero frequencies are meant for the gain to increase. So if we reach a zero frequency, then from negative 20, we would go back to from negative 40, we go back to negative 20, and another pole frequency will send us back to the straight line that we had. Okay, well, let me just start. So assuming we were here, then we reach a zero frequency, a zero pole, a zero frequency like this. Okay, so what would happen is going to be an increase by plus 20 decibel per decade. From what we've learned in the common source stage, we realized that we could use a node to easily identify poles. So if we had a node, then any resistance from the node to the ground, so what we do is that we set voltage sources to 0. So if I set this particular voltage source to 0 by short circuiting it, then I identify this node and try to find out if I can find a pole. So since this is the input, we could call this an input pole, or a pole at the input network, if there is indeed a pole here. So once I can get resistance from this node to ground, so from the node to ground I have resistance Rs, and then from the same node to ground I also have capacitance C in, then I can say that the pole frequency at the input part is equal to 1 over Rs C in. When I come here to the same thing, the resistance to capacitance to ground is CL, and then you can also know or should know that these two nodes are the same. So from this same node to the AC ground, we have RD in parallel with RO. That's if we don't want to ignore channel length modulation, then this would be 1 over this term here would be the pole frequency at the output node. Let's try another example. Looking at this node right here, what will be the pole that we can get from this node? Resistance, so you set all this to 0, then the resistance seen is going to be Rs in parallel with 1 over GM1, because we know the resistance seen at the source is 1 over GM from what we've already studied, all times C in. So this will be the pole. Looking at this node 2, the pole is going to be 1 over RD if you don't want to ignore channel length modulation, in parallel with RO, all times CL. Now what if you come across an interesting case like this? So assuming you are to find a pole of a circuit that sort of has some form of capacitance which goes like this. So let me call this feedback capacitance, and there is resistance here to the input. Okay, and you wanted to find the pole at this node. Now we have the resistance to ground. If I set this to 0, I have the resistance to ground to be 1 over R in, but this capacitance does not lead to ground. So this is the output. So I cannot say this is an AC ground because the voltage here would be changing, unlike the VDD. So assuming there's a resistor here, then the voltage there will be changing. So I cannot say that this is an AC ground. So in the next video, we'll look at Miller's theory and how that would help us to overcome such challenges in identifying the poles. Thank you, and see you in the next video. Bye.